So, paths of charged particles in magnetic fields. So let's do one more application of magnetic fields, which is something I'm going to draw on a piece of paper. So let's get up the document scanner. Okay, so here we are. Okay, so let's draw the path of something in a magnetic field. So I'm going to say that I have a magnetic field that points into the page everywhere. Like that. And I have a little charged particle, and we'll make this a positively charged particle, so we don't have to think about anything complicated here. So all my B's are into the page, and a charged particle has an initial velocity that points up toward the top of the page. So let's try to figure out how this charged particle will move. So I have a positively charged particle in the presence of an external magnetic field, a magnetic field that it did not create, which points into the page. And I would like to figure out the direction of the force. So now would be a great time to pull up those right-hand rules and figure out which right-hand rule you want to use. I can pull up one of these in the beginning. There we go. So for me, I'm looking down here at the bottom. So this is there's only one that has a V in it, and it's this one. So my palm is going to be pointing in the direction of the V. My fingers will turn in the direction of the B, and my thumb will point in the direction of F. So let's do that. So my palm points in the direction of V. So I can think of a vector as starting at my wrist and going to my knuckles, pointing in the direction of V. Now I turn my fingers so that they point into the page. So that will look like that. And the force points to the left. So there will be a magnetic force. Okay, so a short time later, this particle is not traveling straight up anymore. It's going to follow a path kind of like that. So a little while later, it's here. And now instead of going straight up, it's going to be going up and to the left a little bit. So there's my new V. All right, let's figure out the force on this particle. Here's my V. My B points into the page. My thumb points down to the left. There's my new FB. This is a really good test-taking strategy. Do you notice how B, V, and F are all perpendicular to each other? Right? They all make, this is a 90-degree angle here, that's a 90-degree angle here. They always act in either the X, they always act in different planes. So that can always be a good strategy. If you have a multiple choice question that gives you the directions of B and V, without doing any right-hand rules, I know that F is either to the left or to the right. Those are the only two directions that it can be, because it has to be perpendicular to both B and V, just as a little test-taking strategy. Okay, so this is going to experience force. It's going to pull it in that way. And now a little while later, it's going to be here. So my new charged particle is here, and now it's traveling this way. And there's my V. We'll try to figure out the direction of the force here. And maybe you've already seen the pattern, but we'll do it one more time. V is going to point to the left. B turns into the page, and my thumb points in the direction of the force, which is down. And maybe what you see here is a particle traveling around in a circle like that. And if you remember this from last semester, right, anything that's going to travel around in the center of a circle requires a force to cause that centripetal acceleration. And that force always has to point in toward the center of the circle. Now we have a new way to have circular motion. We can have a magnetic force that causes something to point around in the center of the circle. So charged particles traveling perpendicular to a magnetic field will trace out little circles, which is pretty cool. And by the way, this is actually how we eventually figured out that an electron has a negative charge and a proton has a positive charge. A positively charged particle would travel in this counterclockwise circle here. A negatively charged particle, instead of feeling a force to the left here, would feel a force to the right, and it would travel around in a clockwise circle like this. So it wasn't until we could do an experiment like this where we could finally figure out what the sign of different charge carriers was. Oops, I moved to figure out where I was. I think I was here. Yes, I was. Okay. There is that. We've already drawn that, so I'm going to skip through that. This is how the aurora borealis works. So everything travels in a circle when B and V are perpendicular to each other. But you can actually get these like helical patterns, little spirals that will happen if V is sort of neither perpendicular or parallel. So we have a little bit that just kind of travels along in the direction of the magnetic field and a little bit more that goes into a spiral. And I don't need to get too much into the weeds of that. The main reason that I wanted to show you this is so that we could get an idea for how the aurora borealis works. What happens is that you have these high energy particles from the sun, cosmic radiation that comes down, and as they pass through Earth's orbit, they are charged particles moving in the presence of an external magnetic field that they did not create. So they will feel a force. And so some of these charged particles from the sun get trapped by Earth's magnetic field, and they make little spiral actions as they follow Earth's magnetic field lines out of the North Pole and into the South Pole, like that. And so these things have such high energy in there that they actually ionize the air as they travel through the air. And that's why we get these sort of spectacular light shows when sun's radiation is particularly strong, or when Earth's magnetic field is sort of having particularly, it varies a little bit from time to time. And so that can happen with Earth's magnetic field. But mostly this happens, probably almost entirely this happens due to the sun. And you can see here why it's a northern hemisphere or a high latitude phenomenon and not a low latitude phenomenon. So the higher north you get, the more likely you are to see an aurora borealis, because we all know that where the magnetic field lines are closest together, that's where the magnetic field is strongest. So there's a much stronger magnetic field here toward the high latitudes, toward the poles, than there is at the low latitudes. So that's where we see the aurora borealis most. You can do this. So the way that old school TV works is that, and I actually have an old school TV here, so let me get it out for you. Hi, old school TV. It looks something like this. So the way that this TV works is that if you remember, back in the day, we didn't hang TVs on walls because they had this big back. So what's going on here is that there's this big back. And charged particles are being released from the back end, and they're being sent through a precisely tuned magnetic field here. And as charged particles move through a magnetic field, they will feel the force. And some particles are, all of those charged particles are sent to different locations, such that when they hit the screen, if you want to have something blue right here, then a bunch of particles will be sent through a magnetic field that causes all of them to light up blue as they touch the screen. So it's when those charged particles hit the screen that they activate a pigment that makes it be a certain color. And just to prove that this is how it works, I have some pretty strong magnets here. This is a pretty good way to destroy a TV. So let's give it a go and see how it works. I have a magnet here. I'm going to be very careful not to get it too close to my computer so it doesn't ruin my computer. And you can see that as I move this around, it's messing up what was going on with the magnetic field in the first place in a pretty big way. And after I do this, I can even, I hold this for a little while, we've sort of permanently messed up how the computer screen works. Yeah. So it doesn't just go back to normal after you're done. You've messed some things up, right? Like these wires right here. I know there's a lot of glare on my TV screen, but hopefully you can see the difference between the glare and my permanent modifications of the way that this works. Pretty cool. All right. This is also how an electromagnetic flow meter works. So if you have charged particles moving in your blood, as they tend to do, then if you could set an external device that would have a magnetic field through that. And we know that the faster your blood is moving, the larger the magnetic force that these charges will feel. Okay, and what's going to happen is that the positive charges are going to move in one direction, and the negative charges are going to move in another direction. Okay, so we're going to end up with this separation where all the plus charges end up on one side of your artery, and all the negative charges end up on another side of your artery. And the faster your blood is moving, the more this separation is going to happen. So there's going to be a larger magnetic force if your blood is moving faster, and that will mean that the separation is bigger. And just to pull in something that we haven't talked about much recently is voltage, right? A separation of charges. If we had all the positive charges on one end and all the negative charges on another end, we would be able to measure that as a voltage. So you can, with no, totally non-invasively, with nothing but just some sort of external thing that would go around your finger or wherever it is that you wanted to measure your blood, a way to determine how fast your blood is moving, right? The bigger the voltage that you measure when you put it in the presence of an external field, the faster your blood is moving. Okay, so we have just spent an entire week's worth of classes talking about magnetism, and we have not yet answered the very simple question, which is, how does a magnet stick to your refrigerator? So let's talk just a couple minutes about that as we close out the chapter on magnetism. So we've already talked about how ferromagnetic materials, so these are things that are strongly attracted to a magnet and that can be magnetized. These are things mostly like steel. So things that are ferromagnetic have an inherent magnetic moment, which is that right, when placed in the presence of a magnetic field, they will tend to line up like a compass with the North Pole aligned so that the magnetic field comes out of this North Pole of the magnetic moment. And so in a normal ferromagnetic field that is not yet a compass, or not yet a magnet, all of these magnetic moments are just randomly aligned. So this isn't something that would be a magnet. So this is like your refrigerator. Your refrigerator is not normally a magnet. But when you place your refrigerator in the presence of a magnetic field, then all of these magnetic moments will momentarily align with that magnetic field. So your refrigerator is not a magnet, but when a magnet is placed on your refrigerator momentarily becomes a magnet. And then when you remove the magnet, it goes away. This is also, say, how your computer works, which is why you should always keep strong magnets away from your computer, or your laptop, or your cell phone, or anything like that. Which is that, right, the little discs on your computer can create tiny magnets that will stick as those magnets for a little bit of time. So this slide says that, right, they're used to store information on your computer and cell phone hard drives. So there's a little switchable magnet that can store information by just being sort of momentarily turned into a magnet. And we experienced this a little bit, if you remember, when I first introduced magnetism. I got out those paper clips, and when I connected the paper clip to a magnet, those paper clips would stick together. But then I could actually remove the paper clips from the magnet, and they would still stick together, because just for a little bit we were able to induce a magnetic moment and turn that paper clip into a little magnet. And that is the end of what I wanted to talk about on chapter 20. So I'm going to close out this video. Eventually, if I can find it. There it is.